In this session, we're going to see two theorems. One's called the Remainder Theorem, and one's called the Factor Theorem. And we're just going to dive right in. Use synthetic division to find the remainder when the polynomial p of x equals x cubed minus 3x squared plus 5x minus 12 is divided by x minus 4. If you remember your synthetic division, then you know that 4 is going to go into the penalty box because I have a divisor of the form x minus c, and then the polynomial is in descending order, not missing any exponents. So I'm going to put the coefficients 1, negative 3, 5, negative 12 into our synthetic division box thingy here. And the first number comes straight down, and then we multiply and add. So 4 times 1 is 4, add that to that negative 3, we get 1. 4 times 1 is 4, add that to the 5, we get 9. 4 times 9 is 36, add that to the negative 12, we get 24. We were just asked to find the remainder, so the answer is, the remainder is 24. Right about now you're thinking, that was kind of silly. Yeah, we're going to see how that relates to something else. Now let's see what happens when we evaluate p of 4 using the polynomial in the previous example. P of 4 is going to look like 4 cubed minus 3 times 4 squared plus 5 times 4 minus 12. Because remember, when we evaluate, we substitute for the variable. This is going to be, well, let's see, 4 cubed is 64. 4 squared is 16 times 3 is 48. 5 times 4 is 20 minus 12. What do we get here? Oh, let's see here. 64 minus 48 is 16. 20 minus 12 is 8. And for an answer I get 24. That 24 looks a lot like that 24. In fact, the remainder theorem states that the remainder that I get is what will happen when I evaluate the original polynomial for the number that's in the penalty box. So if I divide by x minus 4, then the remainder that I get is the same thing as evaluating p of 4. Make a quick note here. If I had divided by, say, x plus 5, then the remainder that I would get would be the same as evaluating p at negative 5. This is so important that it's a theorem. It's called the Remainder Theorem, and here it is. The Remainder Theorem starts out with, let p be a polynomial function. If p of x is divided by x minus c, then the remainder that we get is what would happen when we put c into p. In other words, p evaluated at c. So let's just reiterate. In the penalty box, if I have a number c, that would indicate that I'm dividing using synthetic division by x minus c. When I put all the coefficients into the synthetic division setup and I get a bunch of numbers down at the bottom, the very last number that I get, the remainder, is what happens when I evaluate p at c. This is actually rather a useful theorem, and our next exercise asks us to use it. Use the remainder theorem to evaluate f of 5 for f of x equals 3x cubed minus 12x squared minus 9x plus 1. So, I'm dividing essentially by x minus 5. But here's the deal. If you're asked to evaluate, for instance, f of 5, that number goes directly into the penalty box. The coefficients of this polynomial in descending order that it's not missing any exponents, are 3, negative 12, negative 9, and 1. That first number comes down, multiply and add, So 5 times 3 is 15. Add that to the negative 12 and I get 3 again. 5 times 3 is again 15. Add that to negative 9. I get 6. 5 times 6 is 30. Add that to 1. I get 31. I can conclude this by saying f of 5 is the remainder 31. Yep, that's all there is to it. That's the remainder theorem. Use it when you're asked to. It comes in handy for other stuff. Now we're going to move on. This next example falls in the category of exploration. Evaluate p of 4 for the polynomial p of x is equal to x to the 6th minus 16x to the 4th plus x squared minus 16. Of course, what this means is we're going to put a 4 everywhere we see an x, the original polynomial. That's what we have here, and then evaluating will give us 4096 minus 4096, and then 16 minus 16. The answer turns out to be 0, so p of 4 is equal to 0. Put that on a shelf for a minute, and now let's divide that polynomial, x to the 6th minus 16x to the 4th plus x squared minus 16 by x minus 4. And since the divisor is of the form x minus c, I'm going to use synthetic division. So I'm going to put 4 in the penalty box, and then the coefficients. Our polynomial is in descending order, but we're missing some exponents. So 1 for x to the 6th, 0 for x to the 5th, negative 16 for x to the 4th, 0 for x cubed, 1 for x squared, 0 for x, and then negative 16 is the constant. I think I want to label these things with the exponents that I just mentioned. This is just for bookkeeping. And, well, let's think about this. We're going to divide something that has x to the 6th by something that's x. Remember, x to the 6th divided by x. The result there would be x to the 5th. So when we divide a 6th degree polynomial by a 1st degree polynomial, we end up with a 5th degree polynomial. The rest of the terms would be x to the 4th, x cubed, and so on down to the constant, and then that last number is going to be the remainder. Remember, with synthetic division, we bring the first number down and then multiply and add. So 1 times 4 is 4, added to 0 doesn't change. 4 times 4 is 16. Added to negative 16 is 0. 4 times 0, well, that's nice. That seemed like a waste of time, but you got to do it for good form. 4 times 0 being 0. Added to 1 gives me 1. 4 times 1 is 4. Bring that down. 4 times 4 is 16. I have a 0 remainder. So we could say from this that the original 6th degree polynomial divided by x minus 4 is equal to x to the 5th plus 4x to the 4th plus x plus 4, and with no remainder. Another way to write this would be that the original polynomial can be expressed as a product of the divisor x minus 4 times the quotient, the 5th degree polynomial. Let me rephrase all of that. We had a 0 remainder that gave us a factor, the divisor x minus 4. When we scroll up here, we see that when we had put 4 into the polynomial, we had an answer of 0. The remainder theorem says that the remainder that I get is the original polynomial evaluated at the number that's in the penalty box. The factor theorem says that if I have a number that when I evaluate the polynomial at that number I get a 0, then I have found a factor of the polynomial, and the factor theorem is what we're going to state next. And the factor theorem says that if we start with a polynomial p, it's a function, that p evaluated at some number c is going to turn out to be 0 if and only if x minus c is a factor of p. Now let's see what's going on here. If and only if means, well, it's a two-way statement. It says if p of c is equal to 0, then x minus c is a factor. And then conversely, if you start with, hey, x minus c is a factor, then you'll know that p evaluated at c is 0. What this indicates to us, though, is, remember the remainder theorem? If I put c in the penalty box and then do a bunch of synthetic division with coefficients and I have numbers down here, then the remainder that I get is equal to the polynomial evaluated at the c that we talked about, right? And if that turns out to be 0, a remainder of 0, then we found a factor. In other words, I can evaluate a polynomial just by using synthetic division. That's the remainder theorem. If that turns out to be a 0, then I found a factor. That's the factor theorem. What we're going to be after is finding factors of the form x minus c, and so synthetic division is a pretty good way to go. All we're after is, does the remainder turn out to be 0? Now, I'll be the first to admit sometimes theorems get in the way of what you're trying to understand, so let me just bring this home. If we have, let me just bring this up here, a polynomial function, let's say p of x is equal to x squared minus 5x plus 4. That can be factored into x minus 4 times x minus 1. If I were solving an equation where, say, this was equal to 0, then I would conclude that x is equal to 4 or x is equal to 1. You would call these zeros. They come from factors. The factor theorem really just formalizes that and says, hey, if you were to put either one of these into the original polynomial, that's how you get the 0. Here we have a polynomial function. Let g of x equal 2x cubed plus 7x squared plus 6x minus 5. The question is, for part A, is x plus 2 a factor of g? It will be if g of negative 2, remember, we've got to change the sign there, turns out to be 0. That's the factor theorem. What's the quickest way to find out if that's true? You could certainly evaluate it, but I'm going to use the remainder theorem. I'm going to put negative 2 in the penalty box because we changed the sign on that thing. And the polynomial is in descending order. We're not missing any exponents. The coefficients are 2, 7, 6, negative 5. Bring the 2 down, multiply and add, right? Negative 4 plus 7 is 3. Negative 2 times 3 is negative 6. Add those together, I get 0. Negative 2 times 0 is 0. Remainder is negative 5. Folks, negative 5 is not 0. The answer is no. X plus 2 is not a factor. Well, let's see what happens with the next one. Part B, is x minus 1/2 a factor of g? I'm going to do exactly the same thing. I'm going to put that 1/2 in the penalty box since it's x minus 1/2. I use 1/2. Coefficients haven't changed. 2, 7, 6, negative 5. And bring down the 2, multiply and add. 1/2 times 2 is 1. Added to 7 is 8. 1/2 of 8 is 4. Added to 6 is 10. 1/2 of 10 is 5. 5 minus 5, or negative 5 plus 5, is 0. So the remainder is 0. The remainder theorem tells us that's what happens when I put 1/2 into g. The factor theorem says that I have found a factor because this evaluates to be 0. So the answer is yes. We can further explore. The original polynomial was 2x cubed plus 7x squared plus 6x minus 5. I have that written down here. And, well, look, the exponents of the original polynomial were 3, 2, 1, and then the constant. So the exponents of the quotient are going to be 2, 1, and then we have our constant. So we can say that this original polynomial is equal to, now x minus 1/2 we found is a factor because the remainder is 0. The other factor is 2x squared plus 8x plus 10. If I were asked to find all the zeros, well, I've just found one, and then I can take this quadratic and either factor it, complete the square, or use the quadratic formula to find the rest. In any case, the answer here is yes, and finding one factor using synthetic division, or long division if you wanted, gives us the other factor.